Hi, here we discuss about a project, design and implementation of a high-throughput multi-channel quantized Gaussian noise generator. Here, additive white Gaussian noise, or AWGN, plays a critical role in wireless communication testing, BER evaluation, channel emulation, and signal processing system validation. While software-based Gaussian noise generation is flexible, it is often too slow for real-time and high-throughput applications. Hardware implementations provide significant speed advantages, but conventional inversion-based architectures require large lookup tables, complex ICDF computations, and multiple leading one detectors when generating parallel outputs. This leads to high logic utilization and increased hardware cost. Quantized Gaussian noise generation, or QGNG, helps reduce precision requirements and hardware complexity. However, when multiple noise samples are generated in parallel, LUT replication and logic duplication still become major challenges. Uniform segmentation reduces computational complexity, but it may slightly degrade tail accuracy. On the other hand, hierarchical segmentation maintains better statistical precision but increases hardware overhead. To address these limitations, this work presents three FPGA-based architectures, fully designed in Verilog HDL and synthesized on a Xilinx Vertex 5 device. The first architecture serves as a baseline QGNG using conventional hierarchical segmentation. The second architecture introduces uniform segmentation with LUT splitting and output shuffling, reducing memory duplication and eliminating expensive segment selection logic. The third architecture proposes an optimized hierarchical segmentation using probability-based LUT sharing and a modified unrolled Galois LFSR, capable of generating multiple uniform random numbers per clock cycle without requiring multiple URNG blocks. Compared to the baseline design, the proposed architectures significantly reduce LUT and flip-flop usage while maintaining high throughput and parallel output capability. Statistical validation through PMF analysis, chi-square testing, autocorrelation evaluation, and BER performance confirms that the generated noise preserves Gaussian characteristics and sufficient tail accuracy. FPGA synthesis results demonstrate improved throughput per CLB, along with reduced area and power consumption, proving that the proposed implementations offer scalable, low-complexity, and statistically reliable solutions for real-time communication and signal processing systems. Now we can verify this paper. This paper presents the three different architecture of Gaussian noise generation. The first architecture is a baseline QGNG using conventional hierarchical segmentation. The second architecture employs uniform segmentation. The third architecture proposes an optimized hierarchical segmentation. This Figure 5 shows two communication system models for AWGN channel emulation. In the conventional model, Gaussian noise is added to the modulated signal before the receiver quantizes it for decoding. In the quantized model, the AWGN itself is first quantized and then added to the signal, followed by a limiter before decoding. This approach reduces hardware complexity because high-precision noise generation is no longer required inside the receiver chain. This Figure 7 shows the conventional quantized random noise generator architecture based on hierarchical segmentation. An 80-bit uniform random number is generated and divided into sign, main segment, subsegment, and subvalue fields. A leading one detector selects the main hierarchical segment, and the LUT provides the corresponding magnitude and threshold values. The comparator and sign logic then produce the final quantized Gaussian noise sample. For this LUT and magnitude generation, we have created a MATLAB GUI developed for magnitude and threshold generation in the proposed QG-NG architectures. The tool allows configurable parameters such as sigma, quantization step size, magnitude bits, threshold bits, and total LUT entries. Based on these inputs, the GUI computes the quantized ICDF values and automatically generates magnitude and threshold data required for FPGA implementation. It also supports noisy LUT creation, CDF mapping options, and exports files in formats like .hex and .coe for direct integration. After file generation, we created a memory file, that memory only used in this Verilog-based FPGA design. This is the Verilog HDL code for this conventional design. This is the simulation results. This is the synthesized report and RTL schematic. Next, Figure 11 shows the proposed parallel quantized Gaussian noise generator based on uniform segmentation. A 31-bit unrolled URNG generates multiple uniform random numbers per cycle, which are used to address split LUTs instead of a single large LUT. Each split LUT provides magnitude and threshold values, and the comparator with sign logic produces intermediate Gaussian samples. Finally, a shuffle network rearranges the outputs to improve randomness and generate multiple quantized Gaussian noise samples in parallel. This is the Verilog HDL code for this uniform segmentation design. This is the simulation results. This is the synthesized report and RTL schematic. Next, Figure 13 presents the proposed parallel quantized Gaussian noise generator based on optimized hierarchical segmentation. An 80-bit unrolled URNG generates multiple random numbers, and a modified main hierarchical segment selection unit replaces multiple leading one detectors to reduce hardware cost. Frequently accessed segments use separate LUTs, while less frequent segments share a common LUT to minimize memory duplication. The comparator and sign logic then produce multiple high tail accuracy quantized Gaussian noise samples in parallel with improved hardware efficiency. This is the Verilog HDL code for this hierarchical segmentation design. This is the simulation results. This is the synthesized report and RTL schematic. Next, here we can verify this all comparisons and we have written an abstract document for this project. Title: Base Paper Abstract. Objective of this work: Existing system. Disadvantages. Advantages. Proposed system. Literature survey. And references. Thank you.
Are you planning to publish your next innovative research in IEEE Transactions on VLSI 2025? Welcome to Nxfee Innovation, where future-ready VLSI research projects are designed with novelty and quality for global researchers. At Nxfee, we provide novelty-based VLSI projects carefully aligned with IEEE Transactions on VLSI 2025. These projects are not yet published, offering you a clear opportunity for unique contributions in top-tier journals. Our research covers key domains like low-power VLSI design, analog integrated circuits, FPGA implementation, signal processing architectures, and emerging applications such as cryogenic front-end ASICs, physical unclonable functions, and self-recycling SRAM cells. Each project comes with a verified novelty, simulation results, and complete customization for your journal publication. You'll find practical design files, HDL codes, schematics, and step-by-step explanations to guide your research journey. We provide 100% accurate results and comparisons of source code with all results, basic documentation, and explanation video. We provide execution support with explanation-recorded video explanations on your system. IEEE guidance for paper writing and journal publication. Affordable project packages with ongoing support. Customization to match your research needs. Early bird offers and discounts for researchers. Don't miss the chance to publish in IEEE Transactions on VLSI 2025. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join Nxfee Innovation, shaping your future for VLSI research. Visit our website today, explore our latest research projects, and get started on your journey to innovation. Join Nxfee Innovation, shaping your future for VLSI research.